Hi, my name is Gabriel. I'm a research associate at Polytechnique Montréal, and I'd like to introduce you to Extremes, a Julia package for the analysis of extreme values. Extremes provides exhaustive, high-performance functions for the statistical analysis of extreme values in Julia, including point and interval estimates of extreme value distributions parameters, 3-parameter estimation methods, tools to deal with dependence including clusters identification functions, support for non-stationary extreme value models, diagnostic tools for graphical validation, and the estimation of return levels and their confidence intervals. The package is largely inspired by two major reference books in the field of extreme values, from Coates 2001 and Berlin et al. 2004. The project was initiated 3 years ago by Assistant Professor Jonathan Jalbert, then most of the development happened during summer 2020 with the work of Marie-Lou Farmer and the help of Dr. Philippe Roy. I am personally a recent addition to the team, acting mostly as a spokesperson for now. Extremes is about to reach version 1, so we thought it was the right time to introduce it to the Julia community. Now, you may or might not be familiar with extreme value analysis, so I'll start with a brief introduction. Extreme value analysis, or EVA, is used to estimate rare events by extrapolating beyond the data range using an asymptotically justified limit model. It is based on extreme value theory, the only statistical discipline that develops a rigorous framework for the study of extreme events. It is used in many fields for risk assessment and impact analysis, including insurance and reinsurance, finance, and most often in climate sciences. Most of the examples I will present today are applications in that context, but please note that Extremes is usable in any context where EVA is required. In Julia, there's only few packages for the analysis of extreme values, despite the growing popularity of the language among scientific community. For example, the package distributions offers the probability distributions object commonly used in EVA, but there is no parameter estimation procedure, and most importantly, there is no analytical framework available for these distributions in this package. In comparison, there were at least 13 packages for EVA in R 10 years ago. So we feel that there's a place for a package like Extremes in the Julia community. My goal today is to introduce you to it. So I'll start with some theoretical notion to better introduce some Extremes functionalities. Within the extreme value theory framework, two classical ways to model the extreme values are the block maxima and the peaks over threshold models. I'll start with the block maxima approach first. In this approach, the data are split into blocks, and we model these block maxima with a theoretical extreme value distribution. For example, the block size often used corresponds to 1 year, so we extract the annual maxima. If the number of blocks n is sufficiently large, the distribution of the maximum can be approximated by this limiting distribution here, referred to as the generalized extreme value or GEV distribution. It's a 3-parameter distribution where mu, sigma, and psi are respectively the location, the scale, and the shape parameter. To introduce this approach within the Extremes package, I'll be using a popular dataset from Cole's book, the annual sea level maxima recorded at Port Pirie in Australia from 1923 to 1987. For this example, the analysis consists in 3 parts. First, we need to estimate the GEV distribution parameters with some estimation method. Then, we'd like to assert the goodness of fit. And finally, we'd like to estimate a return level. Many techniques have been proposed for parameter estimation in extreme value models. Extremes currently supports three: maximum likelihood inference, Bayesian inference, and inference based on the probability weighted moment, or PWMs. For this example, I'll be using the maximum likelihood inference. Extremes provides a function called GEVFit that performs the parameter estimation by maximum likelihood for the block maxima model. It returns the maximum likelihood EVA structure that contains the model information, in this case block maxima, with the data and the model parameters functions. The element theta hat contains the fitted model parameters. Now, once the model is fitted, it's easy to obtain the corresponding wall confidence intervals on these estimates using a simple function cint. Now, we'd like to evaluate if the fit is good. Extremes provides a function diagnostic plots that will draw these four plots: a probability plot, a quantile plot, a density plot, which is the fitted probability density function over the histogram of the data, and a return level plot. I won't perform the analysis of these plots here, but it's easy to see that the fit is very good. Please also note that the theoretical formulation behind these plots is in agreement with extreme value theory and follows the definitions in Cole's book. Now that we are confident in the fit of our model, we'd like to estimate a t-year return level. It's a risk measure commonly used in many applications. It corresponds to the quantile 1 minus 1 over t of the GEV distribution modeling the annual maxima. In practice, it gives the value that is expected to be equaled or exceeded on average once every interval of time t, with a probability of 1 over t. This value is obtained from the quantile function or the inverse cumulative distribution function of the GEV distribution. With extremes, inference for return levels can be obtained with the function return level applied to a fitted EVA structure. The result is encapsulated within the return level structure and is accessible by getting the property value from this return level structure. Now, you may have noticed that the results of the fitting procedure and the estimation of return levels were in different structures. This allows extremes to leverage the multiple dispatch capabilities of Julia and to develop several methods depending on the type of the input argument. For example, the function cint here applied on R will return a confidence interval for the estimated return level value. Another popular approach to studying extreme values consists in modeling the exceedances above a high threshold. Here we fix a high threshold U and we consider only the values above this threshold. In practice, if the threshold is sufficiently high, the exceedances will follow this limiting distribution here, referred to as the generalized Pareto or GP distribution. It's a two parameters distribution where sigma and psi are respectively the scale and the tail index. Now, to illustrate this model with extremes, we'll be using another popular dataset from Coles, the daily rainfall accumulations in southwest England from 1914 to 1962 that you can see on the figure here. For this example, the analysis is done in 3 steps. First, we have to select the threshold and extract the exceedances. Then, we can perform the parameter estimation for the generalized Pareto distribution. And lastly, we can estimate a return level. In extremes, parameter estimation for the generalized Pareto distribution is performed using threshold exceedances, taking values between 0 to infinity. The choice of the threshold here is critical. A too low threshold would lead to biased estimates as the GP distribution is only asymptotically justified, and a too high threshold would lead to very few data for inference, and thus would lead to a very large estimation variance. To extract the threshold exceedances, a suitable threshold can be chosen by examining the mean residual life plot. It can be constructed with the function MRL plot, provided by Extremes. In theory, above a high threshold U at which the GP distribution provides a valid approximation to the excess distribution, the mean residual life plot should be approximately linear in U. Here, it is the case above 30 mm, so we'll use 30 mm as the threshold value. Then, using Julia, it's easy to retrieve the exceedances. Now, we have to estimate the parameters. This time, I'll be using inference based on the probability-weighted moments provided through the function GP_fit_PWM. Similarly, for the block maxima model, this would be through the function GEV_fit_PWM. Like in the previous example, it returns a fitted EVA structure, now a PWM EVA structure that contains the model information, in this case threshold exceedance, with the data and the model parameters functions. The parameter estimates are contained in theta hat. Like previously, the corresponding confidence intervals can be obtained with the function cint, and the diagnostic plots to evaluate the goodness of fit of the model can be displayed with the function diagnostic plots. Like in the previous example, a t-year return level estimate can be obtained using the return level function. To estimate the t-year return level using the peaks over threshold model, the following information is also needed along with the fitted GP distribution: the threshold, the number of total observations, and the number of observations per year. For example, the 100-year return level is computed as follows. It returns a return level structure, and the return level value is accessible using the value property. A key feature of Extremes is its capability to deal with non-stationary sequences. Now, in the case where the sequence of random variables is non-stationary, there is no general formal framework for the analysis of extreme values. Generally, pragmatic methods are used. For example, the parameters of the GEV distribution for each of the maxima may vary because of the non-stationarity of the underlying series. The usual non-stationary model for block maxima is expressed as follows, where the parameters can vary in function of an explanatory variable. From a statistical point of view, it is a matter of identifying one or more explanatory variables that can model the non-stationarity of the parameters. For this third and last example, I'll illustrate the non-stationary model with another popular dataset from Coles, the annual maximum sea levels recorded at Fremantle in West Australia from 1897 to 1989, that you can see on the figure here. This example, the analysis is done in 3 steps. First, we have to suggest explanatory variables to model the non-stationarity. Then we can perform the parameter estimation for the GEV distribution, this time with Bayesian inference. And lastly, we can estimate a return level. For this example, we consider 2 explanatory variables to model the non-stationarity: the year and the Southern Oscillation Index, displayed on these 2 figures. Now, to estimate the parameters under Bayesian paradigm, we use the GEV fit Bayes function for the block maxima model. Non-stationary models can be fitted with the same fit function using keyword arguments to specify the covariates on the parameters. For example, to fit the non-stationary model using the year and the Southern Oscillation Index as the covariate on the location parameter, we simply add the keyword argument location curve ID to the GEV fit Bayes function. This function is simulating an autocorrelated sample from the parameter posterior distribution using the no U-turn sampler extension to Hamiltonian Monte Carlo. This time, instead of theta hat, we have the property sim, an element of type change from the Julia package MAMPA that contains the sample from the parameter posterior distribution. We can see here that by default, the function generated 5,000 iterations, and that the burning phase was 2000 iterations with no thinning, so the final result is a 3000 iterations by 5 parameters matrix. In this case, 3 parameters for the non-stationary location parameter, 1 for stationary phi and 1 for stationary psi. After fitting these models, we should proceed to model selection using a criterion such as the Bayesian information criterion. Unfortunately, this feature is not yet implemented in Extremes, and I want to continue with the non-stationary model to better illustrate the functionality of the package. As I just mentioned, the result is a sample of size 3000 of the parameter posterior distribution in the format of chains of the package Mamba. Then, using your favorite plotting package, it's easy to draw the MCMC chains and to check their convergence. Now, we'd like to estimate return levels like we did in the previous examples. In this case, since the model parameters vary in time, the quantiles also vary in time. Instead, we estimate the effective return levels as defined in Katz et al. 2002. It's the same return level function and it still returns a return level structure, but this time we can see that the values are in a matrix of 3000 by 86. That is the 3000 MCMC iterations and the 86 years of the non-stationary model. Graphically, this looks like this. The dark blue line is the mean of the posterior sample for each year, and the blue ribbon is the 95% confidence interval obtained with the cint function. So this ends my last example. Now I'd like to present additional features implemented in Extremes. Extremes offers useful visualization tools. In my first example, I showed the dynastic plot function, but note that it's also possible to construct each subplot with its own function. Also, a standardized version of the dynastic plot is defined in the case of non-stationary models. In my second example, I showed how to use the mean residual life plot function to select the threshold for peak over threshold models. Now, another interesting feature of Extremes is the tools provided for dependent sequences. Two clusters identification methods are provided to decluster threshold exceedances: the two thresholds method and the runs method. I won't illustrate these functionalities, but there's a complete tutorial in the Extreme documentation on GitHub with a declustering example. Extremes is still under continuous development. Ongoing and future work on the package includes the addition of extremal index to measure the degree of clustering in stationary processes, the addition of other inference methods such as point process or R-order statistics, the addition of direct methods for model selection, and the addition of user-defined prior for Bayesian model, as currently only the improper flat prior is supported. Note that Extremes is not intended for multivariate extremes, but we encourage the development of other packages for the analysis of multivariate extremes in Julia, where Extremes could potentially be used as a building block. This ends my quick introduction to Extremes. To sum up, Extremes provides a collection of methods for the analysis of extreme values in Julia. It was designed to be easy to use by researchers, students in courses on extreme values, but also by engineers who need robust and powerful estimations of extremes. The package has a concise and robust API, and the functionality is tested against known results. As you can see here, there's a pretty good code coverage. There is also a robust and relatively complete documentation accessible on GitHub with a tutorial, and we have submitted a paper that will provide more details coming soon, hopefully. Don't hesitate to contact us. I encourage you to take a look at our documentation and to get started with the tutorial. Thank you very much.